Welcome to Maths with EJD. In this video, I'll be talking about stability analysis in differential equations. That's part of the applications of eigenvalues and eigenvectors, in different areas. In the previous video, I talked about principal component analysis and how eigenvalues and eigenvectors play into that. So here, we want to talk about stability analysis of differential equations as far as eigenvalues and eigenvectors are concerned. So let's know that eigenvalues play a crucial role in determining the stability of equilibrium points, the stability of equilibrium points in systems of differential equations. Okay, so by analyzing eigenvalues of the system matrix of the system matrix, we can predict whether the system will be stable, unstable, or neutrally stable, over time. Okay, so of course the objective here is to learn how to use eigenvalues to analyze the stability uh, of systems of differential equations. So let's take an example of what we intend to do. Consider the system of differential equations. The system of differential equations, dx dt equals ax, where A is a constant matrix. A is a constant matrix. A equals -1 to 1 minus 1. Okay. A is a constant matrix, where A is a constant matrix, this, and X is a vector. X is a vector of system variables. So the system, the stability of the system depends on the eigenvalues of A, on the eigenvalues of A. All right. So, it's more like you have, say, if you want to rewrite that problem, right? You can have it like the x1, the t is equal to, based on based on this expression, right? Is actually equal to minus x1, okay, plus minus x1 plus 2x2, whereas the x2, the t, that's the second column, that's x1, that's x1 minus x2. That's what the system is actually. And from there, you can extract the components of the right-hand side. So now let's see how we can deal with that. So in step one, right? In step one, find the eigenvalues of A. Find the eigenvalues of A. Okay, so we see A is simply -1 to 1 minus 1. And we already know how to find eigenvalues, right? So we know uh, the eigenvalues, right? The eigenvalues are found by solving the characteristic equation, which is that, uh, let me write that apart. That is the determinant of A minus lambda I, which you can also write as determinant of A minus lambda I. I prefer this second one actually, and this is equal to 0. So, so that means that we need the determinant of A, which is -1 to 1 minus 1. Anytime we need to find eigenvalue, this is like a standard procedure, apart from the numerical methods. Then lambda I is actually lambda 0, 0 lambda. Okay, the determinant of that, and that is equal to 0, 0 right here. So that we have the determinant of -1 minus lambda, 2 minus 0, 2, 1 minus 0, 1, minus 1 minus lambda again, and that is equal to 0, 0. So we always do this. So if you look for that determinant, that means we have this the principal diagonal first, this. So we have -1 minus lambda into -1 minus lambda minus 2 times 1, and that is equal to 0. Okay. Oh, why did I put 0, 0 there? This is actually okay as just single 0, right? Okay, this is just 0. Okay. So now we can deal with this. So of course, this is like -1 minus lambda raised to power 2 minus 2 equals 0. So we can square this out. What should I do here? So I can actually say this is -1 plus lambda, okay, all squared minus 2 equals 0. So that this is simply 1 plus lambda squared. This is factorizing minus out there. Minus 2 equals 0. So that means we have 1 plus 2 lambda plus lambda squared minus 2 equals 0. So that we have lambda squared plus 2 lambda minus 1 equals 0. Okay, so if we use the so-called almighty formula, that is quadratic formula. So here you know that quadratic formula, right? Your lambda is going to be minus b plus or minus square root of b squared minus 4ac minus 4, yeah, minus 4ac divided by 2a. That is if you compare this um with a lambda squared plus b lambda minus plus c equals 0. Okay, that's what you're comparing with. So if you do that, okay, so if you do that, it means we are going to have a to be 1, that's the coefficient of lambda squared. B is 2, the coefficient of lambda, and c is -1, the constant. So we have lambda now to be -2 plus or minus square root of 2 squared minus 4 into 1 into -1, like this, divided by 2a, well, that is 2 times 1, so that lambda is equal to -2 plus or minus square root of 4 plus 4. Okay, 4 plus 4. Is that cool? I think so. Yep, that's 4 plus 4 right there, divided by 2. So that lambda is equal to -2 plus or minus square root of 4 plus 4 is 8. 4 plus 4 is 8 divided by 2. So we have lambda equals -2 plus square root of 8. I mean, 8 is 4 times 2, right? So we have that square root of 4 times 2, all divided by 2. So lambda is equal to -2 plus or minus square root of 4 is 2. So we have 2 root 2 divided by 2. So if we divide through by 2, right? So lambda is simply equal to -1 plus or minus root 2. Okay, -1 plus or minus root 2. So that means we have 2 lambda. So we can say lambda 1 is -1 plus root 2, and lambda 2 is -1 minus root 2. So however that goes, so we know that this is positive. This is positive. Why is it positive? Because we know square root of, okay, let me even go all the way, right? Let me go all the way so we can be sure of the positivity. So that means lambda 1 is equal to minus 1 plus square root of 4 is 1.414. Okay, so you can see this is already bigger than that. So it's going to be positive there. So lambda 2 is minus 1 minus 1.414. So roughly. So we have lambda 2 to be, if you remove 1 from this is 0.414. And then lambda 2 is minus 2.414. So you see, this is positive, and this is negative. And for stability, right, those signs really matter. Okay, those signs really matter. So let's go for step 2, where we analyze this whole stability thing. So step 2, so we can analyze stability. Okay, so the stability depends on the sign, depends on the sign of the eigenvalues, depends on the sign of the eigenvalues. So we have the following conditions. Number 1, if all eigenvalues have negative real parts, the system is stable. What that means is that solutions decay to equilibrium. Solutions decay to equilibrium. So that negativity is needed for solutions to decay to equilibrium. That's one situation. The second case is that if any eigenvalue, has a positive real part, the system is unstable. So if any is positive, the system is unstable. The system is unstable. Okay. What that means is that solutions grow over time. Solutions grow over time. If over time, even if one is positive and one is negative, it is still unstable because as one is decaying, the other is growing, and the one growing would most likely overtake the one decaying. Okay. Then we have the third situation. If eigenvalues are purely imaginary, they are purely imaginary. So that means we don't have any real parts. We just have only imaginary parts. So that means we have zero real parts, zero real parts. The system, so we say exhibits, the system exhibits neutrally, neutrally stable oscillations, neutrally stable oscillations. Okay. All right. So if we follow this now, since lambda 1 is equal to minus 1 plus root 2, lambda 2 is minus 1 minus root 2. Of course, we already found this to be 0.414, and we found this to be minus 2.414. Okay, so you can see this is positive and this is negative. So, and the second condition tells us that if any eigenvalue has a positive real part, the system, oh, of course, they are all real. I mean, everything is real. There's no complex parts here. There's no imaginary part. So they are all real. So first of all, they are all real, but then they are now, one is positive, one is negative. And because of that, that makes, so we have to go for that second condition, that if any eigenvalue has a positive real part, the system is unstable. So automatically the system we're talking about here would be unstable. Okay, it is unstable for that matter. So we can now say the presence of one positive eigenvalue, this one, presence of one positive eigenvalue means that the system is unstable. Okay. And in this particular case, now we can even say it's a kind of saddle point, meaning that one might be decaying while the other is growing. So there's a kind of mixture, right? So the key takeaways we have seen here is compute the eigenvalues of the system matrix A, then check their real parts. If all real parts are negative, you have a stable system. If at least one is positive, you have an unstable system. If it's purely imaginary, then you have a neutrally stable, or you can have oscillations. For this example, the system is unstable due to the positive lambda 1, which is -1 plus 2. So that positive part makes it unstable. So that's what we have for that. Okay. That's what we have right there. And for the sake of showing, you may also want to see a Python code for this. So you have just this simple thing. Define the matrix, get the eigenvalues, then check the stability. It is stable if all eigenvalues are less than zero, else unstable if any of the eigenvalues is zero, else it is neutrally stable. So if you click on this now, just like what we found, one eigenvalue is 0.4142, blah, blah, blah. And the other one is -2.4142, blah, blah. And because of this positive one, the system is unstable. So another thing we want to do with this is to talk about the, what is that thing called now? We talk about the phase portraits. It can make you see what's happening with all this. But I'm very sure in the future, I'll be talking about dynamical systems, talking about differential equations. So I'll be talking a lot about things like this. So with this, we come to the end of this video. If you have subscribed to this channel, thank you so much for that. If you haven't, please go ahead and do that and hit the notification bell so you can always get alerted each time a new video is released. Then let me know, comment, let me know if you want me to teach a topic or you wanted to solve a problem or how helpful you think these videos are for you. And of course, like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.